Hey everyone, welcome back. Last time we were studying this concept of work, and we did some computations. We did applications to springs and to chains hanging over the edges of buildings. I want to do a couple more types of examples today. In fact, that's all we're going to do in this lecture is look at some examples of computation of work. So the third type of application that we have is what I'm going to call leaky buckets. So the idea is we'll have a bucket, we lower it down into a well, we fill it up with water, we bring it up, and as we bring it up, water's leaking out. So it's less and less water is in the bucket as we go, so there's an example of non-constant force. It gets lighter as we go. So let me just jump in with an example. So a bucket, and by the way, the wording is a little lengthy here. A bucket has mass 3 kilograms and is filled with 20 cubic meters of water. It hangs from a 30-meter rope. Now, I don't want the rope to be involved in this problem, so we're going to assume that the rope, the mass of the rope, is actually negligible in this problem. So we'll say a 30-meter rope of negligible mass. Negligible mass. How much work is required to hoist the bucket to the top. Yep, I gotta say a little bit more to the top. If the bucket, sorry, I'm not done with my sentence here. Hoist the bucket to the top if the bucket is leaking at a rate of 0.4 meters per second, and the bucket is hoisted. I don't know why I'm using the word hoist here. Reeled in, though. Hopefully you know what I mean. So if the bucket is hoisted at a rate of 2 meters per second. So it's kind of a mouthful here, but here's our picture, right? We've got our bucket here. We're down 30 meters into a well, and we've got some water leaking out at a rate of 0.4. This should say it shouldn't say meters per second. It's leaking at a rate of 0.4 cubic meters per second. So what I want to do to approach this problem is just kind of write down everything that we can get from the problem. All right, so I have to erase part of that, but let's just sort of write down various facts that we can get. First of all, since we're down 30 meters and we're reeling it in at a rate of 2 meters per second, this job's going to take us 15 seconds. So let's just say that. It will take 15 seconds to get to the top. All right, so we'll be done after 15 seconds. Now, remember, as we go up, we're losing water at a rate of 0.4 cubic meters per second. So let's identify how much water we've got in the bucket at any given time. Right? So at time t, there will be, so let's see, how much did we start with? I erased that part. I think we had 20 cubic meters. Yeah, 20 cubic meters. So at time there will be 20 minus 0.4 t cubic meters of water in the bucket. Sorry, there's a street cleaner driving by outside my office here until he goes by. Okay, so at time t there will be 20 minus 0.4 t cubic meters, right? So after 1 second, we'll have 20 minus 0.4 cubic meters. At after 2 seconds, there will be 20 minus 0.8, and so on. Now, one thing to remember, work really doesn't care how long it takes, right? If you take 10 minutes to do the same job that you could have done in 10 seconds, the amount of work that is required does not change, right? So work is independent of the length of time that it takes. So here, I've got an equation in terms of time. I need to convert this to position, to distance, right? So what do we have? We know that we're reeling it in, so the rate is 2 meters per second. So what we have is that t, so let's say, note that, I want to say this, say it like this, x is equal to 2t, all right? We're going at 2 meters per second, so x changes at this rate, x equals 2t, and so if I substitute, right, if I solve for t, I get t equals x over 2, which I can substitute into this equation, and so we'll get 20 minus 0.4 times x over 2, which equals 20 minus 0.2 x cubic meters of water is in the bucket at position x, right? So on our scale here, right, at x, when the bucket gets to that spot right there, this formula tells us how much water is in the bucket. Now, this tells us the amount, but we actually need a force, right? So right now what we have is volume, and so we're going to need this fact. The density of water is 1,000 kilograms per cubic meter, and so the mass at position x is, so what I'm going to do, I've got volume right here, I'm going to multiply it by density, that will tell us the mass. The mass at x is 20 minus 0.2 x times 1,000. And this is the mass of the water. Right? So at position x, the mass of the water is 1,000 times 20 minus 0.2x. Also, the bucket has mass 3 kilograms. So at x, the total mass is 1,000 times 20 minus 0.2x plus 3. And I should say the total mass at x is 1,000 times 20 minus, there's the water, here's the bucket, right? Add those together, that gives us total mass. Now, what we need, we don't need the mass, we need the force. Right, so the force at x is, so let's see now, how do you compute the force? Well, force is mass times acceleration, and so we need to multiply by our gravitational constant 9.8. And so we get the force at x is 9.8 times 1,000 times 20 minus 0.2x plus 3. Right. This formula right here tells us the force, and remember from last time, to find the work, you integrate force. So, final answer, or final setup, work is equal to integral from 0 to 30, 9.8 times 1,000 times 20 minus 0.2x plus 3 dx, right? Here's our force function. To find the work, integrate the force function. And I computed this one. It comes out to be a mess, kind of. Well, not a mess, just it's a huge number. So it is 4,000, no, not 4,000, 4,998,882. Remember, we're working in the metric system, and so the units of work are joules. Right? That's an enormous, when I first wrote this problem, I didn't really notice why I was getting such a gigantic answer. The answer is gigantic because that's a huge bucket. 20 cubic meters, that's a lot of water. All right, so this answer, well, there's the answer. That wasn't very good. So what was I trying to say? It's a funny looking answer. The reason is because in this problem I have a gigantic bucket. That's an enormous bucket, and that's why you've got an enormous amount of work here. The last of the types of examples pumping problems. And so here's the idea. We're going to have some large tank, right, filled with water or some other fluid. And then the goal is to find the work required to pump all of the water or other fluid out of the tank. So let's just start with an example. A conical tank, conical meaning in the shape of a cone, has height 30 meters and radius 10 meters. Find the work required to empty the tank by pumping the water to the top. So let me draw the picture here. Right, we've got a water tank in that shape right there. So it's a cone, and it's got a radius of 10 meters. It's got a height of 30 meters, so this is a very large water tank. And the idea is we want to pump all the water up to the top and just sort of let it spill out. Right, we'd like to find the work required to do this. Now, here's the thing that I want you to be aware of. If you think about how we did the chain problems, these pumping problems are very, very similar. They're a little more involved, but the idea is the same. So if you remember back to the chain problem, what we did is we imagined chopping that chain up into a bunch of pieces and then finding the work required to get each of those little pieces up to the top. Right? By adding all of those little works together, that gave us the total work. We're going to do the same thing here. What we're going to do is we're going to chop the water up into a bunch of slabs of water, and we're going to find the work required to get each of those slabs up to the top, and then that will be our process. So let's take that, slabs like this of thickness delta y, and so let's work through this. And anytime that you get a pumping problem, the first thing you should do, draw a diagram like this, but then what you want to do is draw the two-dimensional picture. I like to arrange things, and there's different ways to arrange it. I like to arrange it so that the top of the tank is at the x-axis, which means that the tip of the tank down here is going to be at -30. So now, if we take a slab here at position y, of thickness delta y, then the two-dimensional picture is going to be here. So this slab right here corresponds to that slab right here. So the first thing to notice, a slab of water, well, it's not a perfect cylinder, but it's roughly cylindrical, right? I mean, it's circular as you slice horizontally, but then it's got these bent sides. So it's not a perfect cylinder, but it's approximately cylindrical. So a slab of water is approximately cylindrical. And so, well, let's think now. Let's say that it has radius a. That would mean that this distance right there is little a. So its volume is approximately equal to, well, how do you compute the volume of a cylinder? It's pi times the radius squared times the height. So in our case, if I the way I've labeled this, I've called the radius a. So we'll have pi times a squared times the thickness, the height, is delta y. Now, notice here that we've got a mixture of variables. I got an a and a y. I need to do something about that. I need to have everything in terms of y. So the next step is to rewrite this equation in terms of just the variable y. Now, to do that, I'm going to use similar triangles. So using similar triangles, what we have, well, okay, so the big triangle, 10, this distance is 10, this distance is 30. And then the smaller triangle, which is, let me highlight it, it's here. Right, these have proportional side lengths, right? The big one versus the small one. And so what we'll get is a over y plus 30. So this distance is a. This distance right here is y minus -30. You always compute distance, larger number minus smaller number. So it's going to be y minus -30, which gives us a y plus 30. And so that means that a is equal to y plus 30 over 3, just solving for a. That means we can say, so volume is approximately equal to pi, I'm going to substitute now, y plus 30 over 3 quantity squared times delta y. So this formula right here tells us the volume, all right, and this is going to be cubic meters. This tells us the volume of a slab of water at position y of thickness delta y. Okay, so we've got volume. I need to convert that to mass and then eventually to force. And so whenever you're dealing with water and you're using the metric system, what you do is you multiply by 1,000, that's the density, and then 9.8, right, that's the acceleration due to gravity. And so the weight, or the force, is going to be 9,800, so that's 9.8 times 1,000. 9,800 times pi times y plus 30 over 3 squared delta y. Okay, so now we know how much that slab weighs, right? We know the force. Now we need to know its distance, and it needs to travel that distance right there, right? From position y up to position 0. And so the distance is, well, it's 0 minus y, which equals minus y. So now the work is going to be, I'm going to pull my constant. In fact, I'm going to, well, no, you know what? I'm not even going to worry about that. Let's just integrate. So the water is from minus 30 to 0. So that'll be my limits of integration. Okay, the way I set up my diagram, we're going from minus 30 to 0. And then it's force times distance. So it'll be 9,800 times pi. I'm going to insert my negative y right there. Then we'll have a y plus 30 over 3 squared. That delta y in the integral becomes a dy. Integrate this. That's going to give us the work. And I just care about the setup here, so hopefully everybody understands the setup. These pumping problems are more involved than the typical work problems, right? These are the harder ones. And so make sure if you have questions, come to office hours. See me. I can clear up whatever kinds of questions, but this is the downfall of virtual learning, right? I don't know exactly what questions you have until you ask them, and you're not in front of me right now. So please come to office hours if you need clarification on these pumping problems especially. I want to do one more example. Of a pumping problem, just because these are usually the harder ones. You'll have some pumping problems on quizzes, on the exam, very likely that you'll get a pumping problem. So you want to be aware of how to do these problems. Okay. Yeah, so one more example. A hemispherical tank with radius, let's do it in feet this time, so radius, we have 4 feet, is filled with water. Now, I usually just do water to keep things simple, but there are other, you can pump other fluids out. Anytime, if you have some fluid, you need to know the density. So if you get a homework problem or a quiz problem or a test problem where it's a different fluid, then the density of that fluid has to be given to you. So this, because we got a hemispherical tank with radius 4 feet is filled with water. Find the work. Required to pump or to empty the tank by pumping the water through a pipe that is, or whose top, let's say it like this, that extends 2 feet above the top of the tank. So let's draw the picture here. we've got a tank now, but it's in the shape of a hemisphere, right, with a radius of 4 feet. But instead of pumping the water just to the top, we actually want to pump it through a pipe, right, that's 2 feet above, or whose top is 2 feet above the surface of the water, the top of the tank. Okay, but it's going to be the same process as the last time. We just have a different shape. So I want to arrange my tank like this, where the top of the tank is right at the x-axis. That means that we're down here at -4, and then we need to take note of the pipe, right, which is 2 feet above. Right, so that's what our diagram should look like here. Once again, if we take a slab of water, it's not a perfect cylinder, but it's roughly cylindrical. The corresponding picture here. If we take a slice of water like that at position Y, thickness delta Y, let's label that A again. So same thing. The volume of the slab is approximately cylindrical, so it's going to be pi A squared times delta Y. Okay. Radius is A, thickness is delta Y. Now, in the last problem, we did similar triangles. In this problem, I'm going to use the Pythagorean theorem, right, because I know that distance is 4. What I have right here is a mixture of variables. I need everything in terms of Y before I can move on. And so I need some way to connect A and Y, and the connection is through the Pythagorean theorem. So the Pythagorean theorem tells us that A squared plus Y squared is equal to 4 squared, so equals 16. And if I solve for A squared, what we get is A squared equals 16 minus Y squared. So that means then that our volume is going to be pi times 16 minus Y squared times delta Y. Now the force right. Okay, so since we're working with feet, you don't multiply by 9,800. If you're working in the metric system, multiply by 9,800. In the US system, the density is 62.5. So 62.5 pi 16 minus Y squared times delta Y. That gives us the force. How far does this slice need to travel? So remember this one. It should be given in your book. They'll tell you what density to use, right? In the US system, if you're working with water, 62.5. If you're in the metric system, it's 9,800. Okay, so there's the force. Now the distance. All right, so how far does this slice need to travel? Well, it needs to travel from Y all the way up to a height of 2. And so the distance, 2 minus Y. So now our work is going to be integral from -4 to 0, right? That's where the water is. It's from -4 to 0. And then we'll have 62.5 times pi. Let me insert my distance right here, so that'll be a 2 minus Y. And then we'll have a 16 minus Y squared times dy. And I really don't care a whole lot about the, I don't take points off if you forget the units, but the units of work in this case will be foot-pounds. Okay, that's a good place to stop. So work on these problems, come see me and ask. They can get confusing, especially these pumping problems. But once they click, right? And then they all go exactly the same way. Okay, so we'll see you next time.